Hello, this is a redoing of my video Arithmetic and Incompleteness, and I want to explore. I have not read Harvey Friedman's book, The Foundations of Arithmetic, yet. It's a very expensive book, and if any one of you wants to reward me, try to get me a deal on that one. I can pay less than what they're charging for the ebook on that. But his thesis, as I understand it, is that for arithmetic to be foundationally complete, you need to get into the levels of cardinality explored by Cantor, the levels of infinity explored by Cantor, which is interesting, okay, because he is affirming arithmetic as a complete system that would transcend any formal system, and yet, in some sense, paradoxically, he says to make it complete, you need to have a formal system. Now, I haven't read the book yet, but what I think he means is that for arithmetic to be complete, you have to acknowledge these levels. My speculation onto what he means is for arithmetic to really be an actual existing complete reality, transcending any formal system, then these levels of infinity would have to be actual realities transcending any formal system. Okay, so I'm not going to put words in his mouth, but that would be the intuition that I have. Now, think about it like this. 2 plus 2 equals 4. We know that that's correct. But we also know that there's no actual axiom that, you can get into the P&O system and try to generate that using some kind of formal system, but really there's no actual axiom that makes that 100% completely true. There's an infinite number of axioms that would. 2 plus 2 equals 4, but it would also have to be the case that 1 plus 3 equals 4. Because 2 plus 1 and then 2 minus 1, so 1 plus 3 equals 4. It would have to be the case that 4 plus 0 equals 4, because you have 2 plus 2 here and then 2 minus 2 here, and that would have to balance out completely. There would have to be a symmetry that balances completely. Literally every single arithmetic statement would have to be true to make one arithmetic statement true. So you would need an infinite number of foundational axioms for arithmetic, which really means there are no foundational axioms for arithmetic. It's not like algebra. It's not like it's not like any kind of formal mathematical system in that way. I want to make this really the last video I do on formal logic, because I want to move on to something to other subjects in more elementary mathematics. I keep promising that. At this time, I'm going to do it. This is a redoing of an earlier video. That's how I'm going to justify it. I want to say why I believe that infinity is an actual mathematical reality, and it's an intuition. If we say that infinity is not an actual mathematical reality, then by definition, we have to have a largest number. And that largest number, or a set with the largest measure, if that's, how you look at it. But I'm going to go at it from the standpoint of a largest number. And that largest number would be n. Well, the measure of a set with well, let's put it this way. It begs the question of n plus 1. What is n plus 1? Well, n plus 1 couldn't exist. Well, if n plus 1 couldn't exist, then we already have arithmetic as being inconsistent. So we already have our fundamental, we have a limit to mathematical reality and a limit to, let's say, even a recursion like this. We wouldn't be able to generate all if not. So if we have the concept of the largest finite number, it would contradict the whole idea of arithmetic being consistent. It would only be consistent up until that largest finite number. If I took that largest finite number plus 1 and then tried to derive 2 plus 2 equals 4 from that, I wouldn't be able to do it. Okay, there'd be a breakdown in the entire consistency of arithmetic. So I would say that the concept of infinity is necessary to even have the concept of the finite, that the two are in some sense in a duality, that if you have finite, you have not finite as a reality that is consistent. It's logically consistent. The concept of the not finite is logically consistent, and therefore it is in formal logic something necessary. It becomes a reality simply by virtue of the fact that it doesn't contradict itself. Also, getting back to Gödel's incompleteness, if we have a formal system with a finite number of axioms, we know that there may well be unprovable truths. Not that there are unprovable truths, but that there are potentially unprovable truths beyond that. So if we ask ourselves the question, how many truths are there in the universe? We at least have to say potentially infinite. And once you say potentially infinite, you've left infinity. You need infinity as a concept to address the question of how many potential truths there are. So anyway, these videos on formal logic themselves feel incomplete, but I think it's time to move on, transition. I want to say a little bit about my background before I do. No, I'll leave that for another video. Thank you.